Hello everyone, my name is Moi Xu. Today I'm going to present our paper, Efficient Maximum K-plus Computation over Large Sparse Graphs. I will first give an introduction, I will show you our framework and show the experiment result. And finally, I'll give a conclusion. So what is a K-plus? A K-plus is a graph where every vertex u inside this graph should miss at most K vertices. For example, in this graph, the subgraph on the left is a T-plus with 4 vertices, and the subgraph on the right is a K-plus with 5 vertices. And our problem is to find a maximum K-plus which size is the largest among all K-pluses of G. And we aim to find the maximum K-plus in G that is of size at least 2K minus 1. And this problem is an NP-hard problem, and most recent algorithms are BNB, Mayplex, and Kplex. All the 3 recent algorithms are following the 2-stage frameworks. So in stage 1, they will produce a reduced subgraph by removing vertices and edges based on heuristically computed Kplex. And in stage 2, they use the branch and bound algorithm to obtain the maximum Kplex in the reduced subgraph. However, they all have some drawbacks in both stage 1 and stage 2. In stage 1, they produce a large reduced graph because both BNB and Kplex only conduct vertex reduction, and Mayplex only conducts edge reduction once, and they all have high time complexity. And in stage 2, all 3 algorithms only use first-order pruning techniques. So to deal with these drawbacks, we design our own framework, which also follow the general 2-stage framework. In stage 1, we first heuristically compute a large K-plus. Then we use our algorithm Coltrane co-pruning to prune unpromising vertices and edges to get a small subgraph. Then we design a algorithm called BB matrix in stage 2, which chooses the smallest degree vertex u from the graph and compute a maximum K-plus that contains u. And finally, it will remove u from the graph and conduct the Coltrane co-pruning algorithm. For the Coltrane co-pruning algorithm, it is designed based on the following 2 lemmas. First lemma is called co-pruning. That is, the minimum degree of a K-plus of size L is at least L minus K. And second lemma is called the trust pruning. That is, any 2 adjacent vertex in a K-plus of size L greater than or equal to 2K plus 1 must have at least 2 minus 2K common neighbors. And based on these 2 lemmas, we can design our own reduction rules. So the first reduction rule is the vertex reduction, which will remove all vertices with degree smaller than LB plus 1 minus K. And the second rule is the edge reduction, which will remove all edges that participate in less than LB plus 1 minus 2K triangles. And LB is the lower bound, which is the size of currently found largest K-plus. And will iteratively remove the vertices and edges based on the 2 reduction rules until convergence. Here is an example of our Coltrane co-pruning. Suppose we are trying to find a T-plus and the current lower bound is equal to 4. So for the vertex reduction, we should remove the vertices with degree less than 3. And for edge reduction, we should remove edges participate in less than 1 triangle. So first, based on the vertex reduction, we can remove vertex V10 because it has degree equal to 1. Then we can remove the edge V3, V5, and V2, V6 because they participate in no triangle. And then after remove these 2 edges, you can see vertex V5 and V6 has degree only equal to 2, and we can remove them based on the vertex reduction. Then we can remove the edge V2, V9. And finally, we can iteratively remove V9, V7, and V8. And the remaining graph will be the reduced subgraph. A naive implementation of the previous idea has a time complexity equal to O R times e to the power of 1.5. Where R is the number of iterations and can be as large as the number of vertices. And we design our algorithm, which is more efficient with time complexity equal to O to the delta G times the number of edges, where delta G is the degeneracy of G. In our algorithm, we first let tau V and tau E be the co-pruning threshold and trust pruning threshold respectively. Then our main idea is to first conduct the trust pruning, and then if there's a vertex U with degree less than the co-pruning threshold tau V, then we'll remove this vertex U and then conduct the trust pruning again. Then let's move on to the stage 2. In stage 2, we design our algorithm called BB matrix. It is based on the following lemma. That is, any two non-adjacent vertices in a k-plex of size L greater or equal to 2k minus 1 must have at least 2 minus 2k plus 2 common neighbors. This means that if we want to compute a maximum k-plex that containing a vertex U, then we can restrict the computation to the subgraph induced by U's two hop neighbors. So if we represent an instance of BB matrix by G, K, S, L, B, where G is the reduced subgraph, K is the parameter for k-plex, S is the currently found largest k-plex, and LB is the lower bound. Then the BB matrix algorithm will first preprocess G by heuristically computing a k-plex. Then it will conduct the contrast co-pruning on G. And finally, it will conduct the BB search to search for a maximum k-plex in the reduced subgraph. And for the BB search algorithm, it is based on 3 types of rules: branching rules, reduction rules, and bounding rules. Branching rules is used to select a branching vertex U. After this vertex U is selected, it will either be included in S or be excluded from G and S. And it will generate 2 different branches. And for both branches, we'll use the reduction rules to remove the unpromising vertices, and we'll use the bounding rules to see if we need to prune the entire branch or not. For the branching rules, we'll have 2 branching rules. The branching rule 1 will select a vertex U with degree greater or equal to the number of vertices in G minus 2. And the S union with U should be a k-plex. And if such U exists, we can see it must be included in the maximum k-plex, so we can cut the other branch that excludes U from G and S. And if we can't select such U, we'll use the branching rule 2, which will select the vertex with largest degree in a set of vertices. This set of vertices will be defined as all the vertices with exactly k minus 1 non-neighbors in S. And if we can't find any vertices, then we'll use all the vertices that are not included in S as this set of vertices. And for the 5 reduction rules, the first 3 reduction rules are based on first order techniques, which based on degree information. And the reduction rule 4 and reduction rule 5 are second order techniques, which consider the 2 vertices and the relationship between these 2 vertices and S. For the first 3 first order techniques, reduction rule 1 will remove the vertex V, which already has k non-neighbors in S. We can see this V will against the definition of k-plex. For reduction rule 2, it will remove such vertex V, well, it is has a non-neighbor U in S, and U already has k non-neighbors in S. And we can see adding V inside S will make U against the definition of k-plex. And the reduction rule 3 is that degree V plus k is lower than the lower bound. And adding such V will not make S has a size greater than lower bound. And for the 2 second order techniques, the reduction rule 4 consider the condition that one vertex U is inside S and another vertex V is outside S. In this case, we check if the upper bound of adding V inside S is greater than the lower bound. If it is not, then we'll remove V from G. And reduction rule 5 consider the condition that both U and V are outside S. And we check if adding U and V inside S has an upper bound greater than the lower bound. If it is not, then we'll remove the H between U and V. And then for the bounding rules, the bounding rule 1 is designed based on the definition of K plus. Bounding rule 2 is designed based on the condition that both U and V are inside the S. And we can see that for the 3 second order techniques, reduction rule 4, reduction rule 5, and upper bound 2 consider all the conditions about the relationship between U and V and S. Then let's move on to the experiments. So in the experiment, we compare our algorithm with 3 existing algorithms, the BNB, Mayplex, and Kplex. We also set 2 variants of the algorithms, which are the BNB-CT and Kplex-F. And the experiment is conducted on 2 different datasets. First one is the real-world graphs, which contains 139 graphs. And the second one is the times dynamic graphs, which contains 84 graphs. The first experiment is on the number of solved instances of a collection of graphs with limited time. And we can see our algorithm can only solve more instances than the existing algorithms. And the second experiment is about the total processing time and the peak memory usage when k equal to 5. And we can see our algorithm is always faster than the existing algorithms and has a lower memory usage than the existing ones. And then for the third experiment, we check the pre-processing when k equal to 5. So we compare the size of the reduced subgraph produced by the pre-process. And our algorithm can always produce the smallest reduced subgraph compared with the existing algorithms. So to conclude that, in this paper, we designed a new framework to compute the maximum Kplex over large sparse graphs. And we also developed an efficient algorithm contrast co-pruning, and we propose a new branch and boundary algorithm BB matrix, which uses the second order techniques in the BB search. And that's all for my presentation. Thank you.